So here we have a problem from engineering mechanics RC Hibbeler. So we have to find the magnitude of F1 vector and the resultant vector. But there is a condition. We have to find that magnitude of F1 vector for which our resultant vector should be minimum. So we can find the resultant vector by this formula and its x and y component by this one. So first we are working for x and y components of F1 vector. So as you can see the y component of F1 vector in its position, and by making the parallel vector concept we are making its x component in parallel. For finding the magnitude of its components you must have to find all the angles to apply sine law. So our first angle is 30 degrees and the second one is 90. We can find the third angle by sum of angle formula. Now we got all the angles, so we can apply the sine law for finding its x and y components. Now we are resolving the F2 vector into its x and y components. The F2 x component is nothing but F2 itself and its y components is 0 because F2 vector completely lies on horizontal x axis. So now we resolve the F2 and F1 vector into its components. And now working for the F3 part. The y component of the F3 vector is already in its position, and by making the parallel vector concept again we are making the F3 x component in parallel. So here we have a slope, so we are converting this slope into its angle. So we can convert this slope by any one of these formulas. So we are taking the tangent formula. By simplifying it we get the angle. But how do we know that the angle came out to be after conversion is the angle alpha or angle beta? Whenever we do the conversion from slope into angle, the angle is always making from its base. That's why the angle came out to be after conversion is the angle beta. And we can find the angle alpha by the sum of angle formula and the magnitudes of its components by sine law. So now we find x and y components of f1, f2 and f3 vectors. So now for the resultant vector, we have to find fx and fy. So for finding fx component, we are adding x component of all three vectors. And for the fy, we are adding y component of all vectors. So for the magnitude of resultant vector, we are taking squares. As you can see, after simplifying the equation, we get two unknown variables. If you look into the question, we have a condition. We have to find the magnitude of f1 vector for which our resultant vector should be minimum. For understand this concept, we are adding all the three vectors by head to tail rule. and our resultant vector came out to be this way. As you can see, by changing the magnitude of f1 vector, our resultant vector also changes. So we have to find that magnitude of f1 vector for which our resultant vector should be minimum. So let's consider this point. At this point, the resultant vector should be minimum. So we have to find that magnitude of f1 vector. So we can find the minimum resultant vector by second derivative test because we have to find its minimum value. So here we are applying some calculus for finding its minimum value. By the second derivative test, we can find minimum and maximum values. So for the minimum condition, we take the derivative of our function and equate it to 0. And the second derivative of the function came out to be positive. So we can say this is for minimum value. So let's consider the function as fr and x as f1. So after equating the first derivative to 0, we can find the value of x, and by putting this value of x in main equation, we can find the function. But always remember the function is nothing but our resultant vector and x is f1. So here are the values of f1 and fr. So now we are applying the second derivative for checking that these values is for minimum or maximum. So by applying second derivative, we get something positive showing that it is for minimum condition. So here are the magnitude of f1 vector for which our resultant vector should be minimum.